In the previous videos, we've been focusing on forces and how forces can interact to give you a net force and then ultimately give you some sort of motion. If there is a net force, there is acceleration. Now today, with this video and the videos to follow, we're going to be focusing primarily on one type of motion, and that is circular motion. And the reason that we're talking about circular motion here is that it is very interconnected with our understanding of forces and our understanding of motion that we've been talking about. So this is a great combination of the units that we've been studying so far. So before we get into circular motion, let's review Newton's first law and this idea of inertia. Newton's first law basically states that a body at rest will remain at rest, or a body in motion will remain in motion at some constant velocity, unless it's acted upon by an unbalanced force. That means that if there's an object moving through space, there is no force acting on it. It is going to continue at the same velocity in the same direction, same speed throughout the entire time. And we've typically talked about Newton's first law as you would need a force to make it go faster, or to slow it down, or to make it move in the first place. But something that we don't always think about is this idea of direction. So I want to start this with an example. In this example, this is based on real life. Most mornings during the school year, I make myself a balanced breakfast of 2 strawberry frosted Pop-Tarts, and I throw them in a plate, and I'm usually running late, so I just pop them on the top of my car as I'm loading things into the car. And there are some times that I'm tired or just in a hurry that I jump in the car and I start backing out of my garage, not remembering that the Pop-Tarts are up there. I don't usually get too far because I'm usually pretty hungry, but say I forgot that they were there and I started slowly driving out of my driveway onto the road, and then my first turn is a sharp right turn. When I do that, there's a good chance that the Pop-Tarts are going to fall off the car. Now, the reason they fall off the car isn't because they're being pushed one direction because of that turn. It's actually because they're not changing their direction. Everything else under them is. That I move my car out from under them by taking that right-hand turn, but they continue along in a straight line. They continue at a constant velocity, speed, and direction. Now, the only thing that would make them move in this circle with me, with this turn, is if there was enough of a force acting on them to cause them to change their direction. Otherwise, they're just going to keep moving forward. Because of this, we need to remind ourselves what acceleration is. If you remember, acceleration is just a change in velocity. But velocity has 2 components to it. It has a speed component, so you could be changing your velocity, you're speeding up, or you're slowing down. And that's what we talked about in our motion unit. But now we're going to talk about the third form of acceleration, and that is changing your direction, because velocity has a direction to it. 2 meters per second this way is different than 2 meters per second this way. If I were to change that, even though the speed is the same, I have fundamentally changed the velocity, so I have had to accelerate in the process. So you actually know some things about circular motion. Without talking about any circular motion equations that we're going to see here in this video and the next, I can present a question to you that you probably know enough math to work your way through. So let's say here that I have this animation of a wind farm. And these turbines are enormous. That if you've ever seen one, sometimes you'll see a truck transporting one of these blades down the road. They're about 30 meters long. They are so big. I would like you to estimate the speed in meters per second of the tip of one of these turbine blades. Now, speed, meters per second, we can calculate just using distance divided by time, meters per second. Now, in order to figure this out then, we need to know a distance and we need to know a time. We know that the blades are 30 meters long, and the tip of the blade is tracing a circle here. That's pretty clear. Also, if you didn't know, use the hint of the fact that we're talking about circular motion in this video. So it traces a circle, and we know that the distance that's traced in that circle is the circumference of that circle. So we can find the distance traveled by the tip in one revolution if we can find the circumference of the circle. Here, the blade goes to the center, so we know that the radius is the same as the blade length. And if we know the radius, we can find this total distance. It's just the circumference of the circle, which you might remember is 2 pi r. So or 2 or pi times the diameter. Either way you could say it. So 2 pi r goes to 2 pi times 30 because the radius here is 30 meters. That gives us a total distance around this circle that's being traveled of 188.5 meters. Now, in this case, it doesn't matter that it's in a circle. That could be 188.5 meters. If you took a string around that whole distance and then just stretched it out, that'd be fine. Now, we know that it travels that whole revolution in the time that it takes the blade to go all the way around the circle. So if we were at a time starting now, going all the way around and stop, we would find that the time for one revolution is about 2.9 seconds. And it's pretty constant, so we can assume that's the same for all the blades as well. Now we have a distance and we have a time. We can plug that into our velocity equation. 188.5 meters divided by 2.9 seconds. And we get that the blades are traveling about 65.0 meters per second. That's crazy fast. And that's just at the very tip of the blade. It is not moving that fast in the center. The tip is moving much, much faster. So without discussing any circular motion equations, you can work your way through a lot of this stuff just by understanding the idea of circumference, the idea of timing things in a circle, and you can work your way to this answer. But let's look at some of the equations that are going to become important. And as part of this, some of the variables that we'll be defining are actually using radians. This does not mean that you will ever use radian mode on your calculator here, because we're still not going to use radians in trigonometric functions like sine or cosine. So you're still going to want to be in degree mode for everything on this test. But radians can help us define how far around the circle something has traveled. So if you were to walk around the circle once, you could find your total distance just like we did on that wind turbine example. You would need to know the radius though. So if I said the radius of the circle is 1 meter, the circumference is just 2 pi r. 2 pi times 1 meter is 2 times pi. 3.14159 will give us about 6.28 meters. Now, this equation is pretty versatile, right? Like, as the circle grows, we expect that the circumference is going to grow as well. And the only difference is swapping out this radius. If this were instead 5 meters, this 1 meter would turn into 5, and then you could recalculate it and have it be 31.4. You can do the same thing for any radius value. If it was 100 or a million or a trillion, you would just be swapping out that one value, which means that this format is pretty flexible, and we can make it super flexible if we instead just give this a symbol. And we say the radius is r. We don't necessarily know what it is, but this could define any circle that we see, and if we do know the radius of the circle, we can then just multiply it out and figure it out later on. But for now, we're just going to use a placeholder. We're going to call this r. And this r, rather than giving it a measurable distance like we would do with meters or some other unit, we're going to call it based on how far around the circle it's going. We're going to give it the name of a radian. Now, if you took this radius as your unit now, no longer are we saying meters or centimeters or kilometers. We're saying that the unit is the radius. And when we're defining that, we could then just figure out how many of those radii, can fit around the circle if we were going to go end to end. And each one of these, we're going to kind of say like an angle. And in your math class, you might just talk about radians as angles. 1 radian is if you took the radius and just laid it across the circle. That means that going around here, we're going to get 2 pi radians. It's just the placeholder here in our circumference equation. So 1 circle is 2 pi radians. With that in mind, you should be able to solve some problems like this. If you had a child on a merry-go-round rotating 3.5 times, what's their angular distance in radians? So think about what's happening. They go around once, twice, 3, and then a half. Each of these full revolutions are 2 pi radians. And then the last one is just pi radians, it's just half of that. So we can say that 3.5 times 2 pi, 1 full, will give you 7 pi. If you multiply that out, it's about 22 radians overall. So we can do the same thing just backwards. If you said, here you have an ant on a record player, it spins for an angular displacement of 14 radians, how many revolutions has it experienced? That should really say angular distance, I suppose. 14 radians, how many revolutions? Each revolution is 2 pi radians, so just 14 divided by 2 pi will give you just over 2.23 full revolutions that are acting. So you should be fairly comfortable with this idea of a circle can be defined as 2 pi radians. We're going to get back to this in a little bit. It'll just be a nice placeholder for us so that we can talk about it as a generic circle rather than one that we know the exact value for. The other piece that we need to kind of lay the foundation and the groundwork here is the ability to time circular motion. What we did in that video or that animation of the wind turbines is we figured out how long it took the blade to go around one complete time. Now that actually has a very specific name in physics. We call that the period. The period is the time for a complete revolution. So it doesn't matter if you're talking about a wind turbine blade or a horse on a merry-go-round or something like Earth that's spinning. The period is how long it takes to go around once. We are going to give this a symbol of capital T. So lowercase t is just generic time. Capital T is the period. It's the time for one cycle or one complete revolution. Since it's a time, we're going to measure it in seconds. So that's going to allow us to talk about this idea of angular velocity. What we calculated in our turbine example was velocity in meters per second. That's how fast it was going, meters per second. But that's kind of a linear idea because linear motion, you're just taking distance divided by time. And that could be the same if you were moving in a straight line or if you're just figuring out the total distance you're going around the circle. There is another way to define how fast something is moving, and it's based on how many times does it go around per second. That you could have a really high linear velocity, but have it not moving around the circle very often. So for example, if you're looking at the linear velocity of a planet like Earth, it is moving very, very fast. Or I think it's like something in the order of 10,000 miles per hour. The Earth is revolving around the Earth, or around the sun. But as an angular velocity, so like how much is moving, like how many revolutions it makes, it only does that once a year. So it's pretty slow. We can define this angular velocity for circular motion by taking the angular distance divided by the time. So not this linear idea of meters, but how much of the circle it's swept. Now, to find circular motion angular velocity, we're going to use a special symbol. Now we call, this is actually the Greek letter omega. It's the lowercase version of omega. It looks like a curly W, but it's actually a lowercase omega. And we call that the angular velocity. And that's going to be in radians, our angular distance, divided by seconds, our time. So angular velocity, radians per second, is this omega, funny looking W symbol. Now, if we know that we're talking about a single revolution, we can define this even further because this angular distance over time, a single revolution, is, we know, 2 pi radians. So that's the radians part. And we know that the time we're going to define as t. That's the time for one revolution. So if you have a single revolution that you know the numbers for, you can just say that's 2 pi over t. That'll be equivalent to your angular velocity omega. So with this in mind, we can calculate in a couple different ways this angular velocity. Say a Ferris wheel takes 40 seconds to make a full revolution. What is its angular velocity in radians per second? Again, if we know that it's just one revolution, we can use this simplified version and say it's 2 pi. That's the radians that it went around for one revolution. And the time is the time for one complete revolution. That's the period, 40 seconds in this case, because that tells us that it's for one revolution. We can plug that in and say 2 pi over 40 is 0.157 radians per second, or radians seconds to the minus 1. Again, 2 pi radians, that's the full circle. 40 seconds is the time. So it's how many radians per second. Next, a car tire rotates with an average angular velocity of 29 radians per second. In what time interval will the tire rotate 3.5 times? All right, with this in mind, we can say, all right, omega is just angular distance over time. We're not given necessarily one revolution. It says it went around 3.5 times. So I'm going to use a more generic definition of just how many radians total divided by seconds. And I am given an angular velocity here, 29 radians per second. I'm going to plug that in for omega. And then my angular distance is 3.5 times 2 pi, 3.5 revolutions times 2 pi for one revolution. That is a number in radians. That's my total radians divided by the time. Then I just need to solve for time. Time is 0.758 seconds. There is another way that you can actually do this problem. If you really like the idea of just focusing on one revolution, you can use this equation as well. So omega is 2 pi over t. You can plug in this omega is 29 radians per second. 2 pi is your angular distance. And then capital T is the time. If you solve for capital T, you'll get 0.217. And you notice this isn't the same time as what we just calculated because that's the time for one revolution. And this tire is rotating 3.5 times. So I can just multiply that by 3.5 and I end up with the same 0.758 seconds. So there are a couple different ways that you can go about solving that problem, but you should be able to find the time interval for a tire to rotate if you're given how fast it's rotating in radians per second. So let's go back to this idea of linear velocity then. Remember, angular velocity is just how many radians you're sweeping per second. It doesn't matter on how big the circle is. Linear velocity does. At any given point, an object in circular motion will also have an instantaneous linear velocity. If you're doing donuts in a parking lot, your car isn't going to tell you how many radians per second you're moving. It's going to say like, no, you're going 20 miles per hour. It's going to give you a linear velocity, just a linear distance divided by time. This velocity will always be in the direction tangent to the curve. If you're not comfortable with that idea, let's look at an example. Here we have a merry-go-round, a carousel. These horses, I like this example because these horses are always facing tangent to the curve. So like if for some reason this horse was like to break free from this circular prison that he has to run around forever and ever, this horse is going to just continue off in a straight line. Say this is like a merry-go-round of death, and then it goes really, really, really fast until one of them breaks free. That's what it's going to look like. So here's a top view of that merry-go-round. And we have it spinning. If I were to stop it, these horses are going to travel along at the direction that they were facing at that moment. So they're going to move tangent to the curve. That is my linear velocity. And I can calculate linear velocity, again, using this velocity is distance over time. That distance is 2 pi r. It's the circumference of the circle. It's the distance around the circle to make one complete rotation. Time is then just capital T. It's the period, the time to complete one complete rotation. Now, this equation isn't new. This is what we just did in the turbine problem. You were able to figure your way out through this understanding of the circumference is how far you're going. Now, if we take that equation, you'll notice that this omega equation for one revolution shows up in there. That 2 pi over t shows up right here. So I can rewrite this by plugging in omega. And I get v, the linear velocity, is equal to omega, the angular velocity, times the radius. Remember how I said that this idea of radians is just kind of a placeholder until we know the radius of our circle? Well, that's the case here, that this radians per second is a generic, this is how many times you're going around the circle per second. But if you know the radius, all you need to do is multiply it by that omega value, and it pops it out in meters per second, or some sort of linear velocity. And again, the size of the circle is going to change your linear velocity. This is the equation that actually shows up in your physics data booklet. V is equal to omega r. The linear velocity is equal to the angular velocity times r. Now, angular velocity actually isn't given in your data booklet. You need to know that it's angular distance over time, or if for one revolution, 2 pi over t. The easiest way to remember is just to remember the units. Angular velocity is in radians per second. So figure out how many radians is traveled per second. All right, one last scenario with our carousel. It goes one complete rotation every 10 seconds. That's what I have it animating here. We can find the angular and linear velocity of each row. The angular velocity is going to be just 2 pi over t, because we know the time for one rotation was 10 seconds. So 2 pi is one complete revolution in terms of radians. So for this A row, that inner row, we can calculate 2 pi over 10 is 0.63 radians per second. The linear velocity is just that omega times r. We could go back and figure out the circumference and all of that stuff like we did with the turbine. But here, since we already know omega, we can just multiply it by r. It's 2 meters from the center of the circle, and we get 1.3 meters per second. I'd like you to do the same thing to calculate omega and v for the outermost row, b here. You'll notice here that omega doesn't have a radius in it. So omega only depends on how fast it's going around, and they're all trapped in this carousel of doom, so they are not going faster than the inner row as far as how many times it goes around the circle. So that's still 10 seconds for a complete revolution to give you 0.63 radians per second. Now, the velocity, linear velocity, does actually change, and that's multiplying by 3 instead of 2 to give 1.9 meters per second. So this gets me to a scenario that I think about a lot. When I was younger, I watched a Sesame Street Christmas special, and there was one scene in that they're all skating in a circle, where they're making one big line and trying to go around the circle. And as they got going faster and faster, the outermost Muppets in this Christmas special started peeling off because they were traveling way faster than the innermost. If you ever tried to walk a line and keep a line straight as you went around a corner, those of you in marching band might be comfortable with that idea. But going around a corner, the innermost part of that corner doesn't travel very fast, but the outermost, they're booking it, taking as large of steps as they can to keep that line straight. The outermost has to travel a lot faster. That's why this carousel here, the outermost, actually go faster. So if you're looking for a thrill, get as far away from the center as you can on a carousel, and you'll feel the wind in your hair travel a little faster. I want to finish off with just a couple more examples so you see some more. If you're sitting 4 meters from the center of the carousel, your radius is 4 meters, and that carousel is spinning 12 radians per second, and you throw a ball in the air, how fast will the ball continue in a straight line? 12 radians per second is important for you to recognize is an angular velocity. That's omega, is 12 radians per second, which means we are going to use this equation here. Linear velocity is just omega times radius, and that's 12 times 4, or 48 meters per second. Using this same equation, v is equal to omega times r, I would like you to find this next problem. A woman passes through a revolving door with a tangential speed, so she's moving at 1.8 meters per second. If she is 0.8 meters from the center of the door, what is the door's angular velocity? So using that same equation, I can just identify what these variables are. 1.8 meters per second is my velocity. That's v, not omega. Omega is in radians per second. The radius is 0.8 meters, which means in this equation, if I plug it in, I got 0.8 is equal to omega times 0.8, or 1.8 is equal to omega times 0.8. Solving for omega, I get 2.25 radians per second. So with all of this in mind, you should be pretty confident with a couple different things. You should be able to convert angular displacement, or between angular displacement and revolutions, in radians. So the idea that one time around is 2 pi radians. You should be able to define and measure the period, capital T, of circular motion. Just time it as it goes all the way around the circle, and that is the period. Capital T is 1 revolution, lowercase t is just overall time. You should be able to calculate angular velocity, knowing that it's in radians per second and not meters per second, and then calculate and describe the tangential velocity based on angular velocity and radius. You should also be able to do it like we did in the turbine problem, using the circumference and the time to kind of work your way through without an equation that's generally in your data booklet.